That a thing? Seriously? No, you.
Yeah.
Because he's a hippie.
But eventually your hair will get like
Shower in a bottle. So when we learned this in Algebra 1 and at the beginning of Algebra 2, we tend to just stay with one particular type of radical called a square root. And that was what your Delta Math assignment yesterday. Hope you got that done. You can do it still today if you want, but that's what that assignment was about, was simplifying roots, but only a particular type of roots, square roots. I'm going to pause this real quick. Nice. So let's do just a quick review. I hope you are good with your roots. We're going to introduce a bunch of new lists of numbers today. And you guys, especially you ninth graders, have seen them. You're more familiar with them because we did a little more with this last year in your Algebra 1 class. So, but anyways, just make sure you're up to speed. So if I put up something like this, you know that that's called a square root. And there's a very select list of numbers from which you choose. So if I said I want you to simplify like the square root of 84, then you know that you're going to look only in the list of numbers that we call squares. 4, 9, 16, 25, so on and so forth. Hang on, I have to pause this again. So we're back. So when we break down a square root the way, we are supposed to, then we break it into two roots, but we have to look at the list of numbers that is called squares. And you already know that this breaks down tree-wise into this. Remember, don't ever just put numbers, put two blank roots, and then it's going to be 4, and it's going to be 21. And then, of course, the square root of 4 is 2. And why can't we break down the square root of 21? Yeah, his only factors are not square rootable. And so remember, we can only consider it like I can go further if it contains something that can be rooted. So that's not what we're doing today. Like, I know you know how to do that. And there'll be some of those, handful, 4 or 5 sprinkled throughout the assignment. But the assignment really consists now of higher level roots. And so you're going to see today cube roots, fourth roots, and fifth roots. So those are the kind of higher order radicals, we say. So let's say I asked you for the cube root of 8. Using your resources, your brain can be a resource. That cheat sheet that we've made can be a resource. But at some point, you'll just memorize a bunch of this kind of stuff. Do you guys know offhand what the cube root of 8 is? It is undoubtedly 2. So where we're going to go today is we're going to start thinking about breaking down higher order roots using trees, just like we do with the second degree, the square roots. So I made myself a note, because sometimes I get a little carried away, made myself a note to make sure that I don't press on until I make a list of cube rootable numbers. So you remember that we have a list of the squares, 4, 9, 16, 25, 36, 49, so on and so forth. And that goes pretty far out. We're going to make now a list of cubes. And so again, ninth graders, this will look more familiar to you. So these are cubes or third powers. You can call them cubes, or you can call them third powers. I'm just putting third powers because the next one we don't really have a name for. So we're just going to be consistent. Second powers, third powers, fourth powers, fifth powers. So the third powers consist, of course, of 8. Because if you take 1, or 1 is the first one, if you take 1 to the third power, you get 1, right? And that's never a useful number for us. So every list that we do is going to contain the number 1, but we're not interested in that. So what is 2 to the third? What is 3 to the third? What is 4 to the third? What is 5 to the third? What is 6 to the third? What is 7 to the third? What is 8 to the third? What is 9 to the third? And what is 10 to the third? Good. And generally we don't go past that point. And you'll just be more fluent mathematically. I don't disagree with using calculators to some extent, but you'll just be more mathematically fluent if you take a few moments here and there to just let yourself start memorizing this stuff. And then you don't have to type so much stuff in. They're going to come up. There's a lot of times today where we're going to type in like, can this be divided by 3? Can this be divided by 4? And I fully understand that. So anyways, those are called cubes or third powers. And let's head on to the next list now. Let's talk about fourth powers. Say again. It should be. I think everything that we're going over today is on that. That's why I set out a nice fresh stack of them today to make sure that you all have one. So fourth powers, where do they always start at 1. What's 2 to the fourth? 3 to the fourth? 4 to the fourth? 5 to the fourth? 6 to the fourth? 1,296. And do we have any more than that? You could make some more, couldn't you? Generally, there's always like this practical sort of stopping point. There's a point where we're like, we could go further, but we just don't generally see numbers that go past that. So that's a good place to stop. And the only other one that we're going to talk about right now, I mean, we could continue the lesson at some point ad infinitum. Like you could go to 6th and 7th and 8th powers, but it kind of loses its practicality. So the next ones are 5th powers. And again, 1 to the 5th powers, of course, 1, 2 to the 5th, 3 to the 5th, 4 to the 5th. And again, we kind of feel like, yeah, could we go further? Like, what's 5 to the 5th? 3,125. So yeah, I mean, you could keep going, but again, there just comes a point where you go, nah, I'm good to go. So what we're going to do today is we're going to muddle around in these lists, and we're going to tinker, and we're going to simplify radicals that aren't on this list, but that contain factors that are on this list. So I have 12 examples and 9 examples for you. If you feel like you need some more, let me know. And then the assignment is on paper. Delta Math doesn't do a very good job with this particular topic. So I had to supplement it with one of those CUDA worksheets. So let's get to it. And we'll run through them in a very specific order. So I have a cube root, a 4th root, and a 5th root that I think are more easy. And then I have like a medium, and then I have a harder version of each. So one thing I wanted to say before we get started is I didn't have this in my note card, but I wanted to mention this. Can you do, without using imaginary numbers, can you take a square root of -16? No. It's 4i. So without using imaginary numbers, this is not defined. The square root of a negative number is not defined. However, and you know from the tone of my question, can you take the cube root of -8? You actually can. And I know that we tend to think like you can't root negatives, but you can if it's an odd index. The fact that this is an odd index means this is possible. This means that I can actually take -2 to the 3rd power, and look what I get. I get -8. And so roots are evaluatable with negative radicands, that's the stuff inside, provided that the index number on the outside is odd. But again, if I hop it, if I skip from, remember this was a 2nd root, this one is a 3rd root. If I hop up to a 4th root now and say, can you do the 4th root of 256 or -256? The answer is no. Any even index root does not exist in the real numbers if the number inside is negative, because by definition, you literally cannot take any number and raise it to the 4th power and get -256. And being in a high school class, you should agree with that. Like, if you multiply something by itself 4 times, it's always going to come out positive, right? So as we go through the lesson today, bear in mind that you will see negative numbers inside the roots, but only when the index, the flavor of the root, is odd. Good. Glad we had that little talk. So let's get to it. The first one I have for you is the cube root of 16. And I'm going to show this to you today. I find this to be a cleaner process if we do this without a tree. I'm going to kind of make the tree, but inside of the root sign, the radical. So the first thing you always do, is to check your lists. Then you've got that wonderful cheat sheet there where you can look and see right now, is 16 a cube rootable number? It is not. Does it contain a cube rootable number? Yes, it does. And what is that number? It is 8. So what we're going to do is we're going to break the cube root of 16 up into the cube root of good guy, bad guy. This is not arbitrary. You don't get to just pick some math fact out of your bum, say, oh, I just like 4 times 4. It's got good vibes. You have to pick a number that is going to be favorably rootable based on the situation, right? And I focus on this because what is the cube root of 8? So what happens is that guy becomes what I like to call a jailbreak. And so when you take the cube root of 8, it comes out front and becomes 2. And then what's left over? The cube root of 2. Good. So basically what we're trying to do here is we're trying to pull whatever we can out of the root, but we have to now adjust our thinking and go to different types of lists. So sometimes we pull from the list of squares, sometimes we pull from the list of cubes, so on and so forth. Does that make even an ounce of sense? Yeah. Fantastic. Let's talk about the 4th root of 405. Yeah. Not much to it. It becomes a bit more of a patient process at times when the numbers get a little bigger. So 405 is not a 4th rootable number. If you look at your list of powers of 4, it said that wrong. At your list of 4th powers, you're not going to find 405 as a 4th rootable guy. So this is where you start experimenting. And I do, understand that you're going to type some experimental math facts or division facts into your calculator. So can you think of anything that is a power? 81 is. Yes. And it just so happens that if you were to take 81 times 5, you would get 405. So just like we have been with square roots, I mean, if you wanted to see this, if you want this to look more familiar, if you're a tree person, then yours would look, yeah, if you're a tree hugger, that's a good one, Kevin. Then yours would look like this, right? It's just like we do with square roots, only we have different indices, like different flavors of roots. And so like I could make it look like this, the 4th root of 81 times the 4th root of 5. So if you still want to embrace that tree idea, you can keep doing it that way too. But anyways, what is the 4th root of 81? It is. And that guy becomes, again, a jailbreak. So he is out in front now, free, busted out. And what's left over? Nice. 3 times the 4th root of 5 is the answer. Yes.
What does that mean? It doesn't. Why is such a big? Because it's a new topic. It's still breaking down.
Resume. Felt good. I'm back. Say again. I know, right? Pause. Yeah, true that. So I start cooking through these 5th root of 729. First thing, again, you always want to check is 729 just straight up 5th rootable? And it's not. I haven't put any of those on here. So you can look, and you should always look, but I'm not going to give you any right now. So I'm going to stick to this formatting. I'm going to keep it as the 5th root, and I'm going to keep it like in-house, as they say. So I'm going to take 729 and bust it up. And really, it's just you experimenting and trying to, this isn't arbitrary. You're dividing only by numbers that are on the list of what we call 5th power. So like you're dividing by 32. That's 2 to the 5th. 3 to the 5th is 243. You're dividing by a very select list of numbers to see what works. Did you find it? It does work. Good. So 243 times 3. That would normally seem like a completely useless multiplication fact, but we care because 243 now is a good guy to us because he's fifth rootable, and that's kind of the cloud under which we're working here. So what is the fifth root of 243? Good job. So this 243 that I'm circling in red becomes the jailbreak. He becomes a regular 3, and then what's left over is times the fifth root of 3. Okay, those are kind of my easy level ones. Let's hop down. Everybody okay on that? All right, let's head down. We'll head down a row here. This next one is going to be 4 times the cube root of 135. So the reason I made a second row here is because I wanted to talk to you about the numbers in front. And you've seen this before. What concern do we have with the number in front? It's already a jailbreak. You guys are all saying great things. You just flip and ignore it, right? So like that 4 can basically be put on timeout for a while we go and do the actual math problem in this yellow box. The 4 can just wait. So it's a jailbreak that will eventually multiply by the next jailbreak that pops out. And so my focus is the third root of 135. And again, you're very robotically going and attacking that and dividing only by the numbers in the second list. What'd you find? Say it again. Good man. So what the problem looks like now is it's still 4 times the cube root of, but again, inside I'm taking the number 135 and I'm breaking it into pieces, 27 times 5. There's more ways than that to make 135, but as I've always said with roots, you should only care if progress is to be made. Like, can I root something? And of course, yeah, 27 is a good guy. So what is the cube root of 27? So he becomes a jailbreak now. So what I have is an already outside jailbreak who's going to have to multiply by a new jailbreak. You could have totally just put 12. I just was hesitant to put 12 because someone probably would have said, where'd you get 12? So, so the 3 is a new jailbreak. And then what's left over is times the cube root of 5. And if you're more comfortable, you can put a time sign. There's a little blue arrow up here. If you like putting a little dot time sign there, that's totally fine because sometimes it just looks like it needs it. So anyways, the final answer to this one would be 12 cube roots of 5. Where we're headed with this eventually is we're going to start doing this algebraically, and then we're going to start adding and subtracting radicals. So the first skill we have to have in line is, can we just break them down? Like, can we get them down to their like core DNA, so to speak? Next one is 2 times the fourth root of 112. So I'll give you guys a moment on that. The index, because if we put it on the right side, it would look like an exponent. So like if I didn't put it right here, if I put it up here, then that would actually mean the square root of 112 raised to the 4th power. So when we want to label a root by its flavor or its type, what we call it the index, that's why we always put it right there. Yeah. Did you guys find the multiplication combo that makes 112 that we care about? What is it? It is. Very good. So inside, we're going to rewrite the problem as 2 times the 4th root of 16 times 7. And this time I'll kind of do what Gavin hinted at last time and just maybe skip a little bit of work here. So what is the 4th root of 16? It is 2. So that jailbreak of 2 is going to multiply by the pre-existing 2, giving us 4 times the 4th root of 7. So you kind of got to decide, which one do you like better? Like, do you like the way this blue one looks, or do you like the way this green one looks? Like, you'll notice I added a little time sign. You just kind of, it doesn't matter. Nobody really cares. You got to pick. Easy peasy so far? Yeah, good. So let's do -8 times the 5th root of 64. You won't find this to be any more challenging than the last ones. You should find this one like almost instantaneously. Yeah, 32 is our guy. So what's hard about this is you got to keep jumping lists. You got to go from the square list to the cube list to the fifth power list to the fourth. So you got to have that resource handy there for sure. Always keep that around. So we have -8 times the fifth root of 32 times 2. And we're breaking it into 32 times 2 solely for the purpose of breaking the 32 out of jail. What is the fifth root of 32? And when that jailbreak multiplies by the pre-existing jailbreak, what do we get? Times. Good. What's the verdict? Do you guys like the little time sign or no times? I mean, if I put the little dot here, is that yay or nay? No? Just leave it out. Okay. I just didn't know if it would bother you guys, so I'll leave it out. Doesn't matter. All right, the last row, these will only be a little bit more challenging because of what's going to be inside. So we talked about this about 7 or 8 minutes ago, so you should not panic at all. So let's do -3 times the cube root of -250. So the reason I said what I said a while back is because I didn't want you to think that this is like, I can't do this. You can do this because the cube root exists and is fine with negative insides. Third roots, fifth roots, seventh roots, any odd root is doable with negatives. So any thoughts on how we're going to break up the guts of it, the inside? Definitely the right idea. Yeah. But 125 times 2 doesn't make -250. That's the key. So make sure that the number that you're going to break out of jail is your negative. So when we divvy up -250, we specifically want -125 because that negative number we want to bust out. That's part of simplifying completely. So when you take the third root of -125, you don't get 5. You get -5. And when that -5 breaks out of jail and multiplies by that -3, it does become a positive 15. And then times what? Cube root of 2. Very good. Okay. 2 more, and then it's off to work time, okay? -8 times the fourth root of 1,875. Seems kind of annoying and big, but actually there's a very limited pool of numbers from which to choose. So with your calculator, you start dividing it by only the numbers that you care about. Right, 16, 81, so on and so forth. And you found it? 625 times 3. Good. So we're going to write -8 times the fourth root of 625 times 3. If you don't have a good grasp on the lists and like where to look, this will be the hardest assignment you've ever done. If you do, it's like, I got this. Just relax, it's cake. What is the fourth root of 625? Good job. And that 5 breaks out and multiplies, and what do we get? -40 times. Well played. All right, guys, last one, and then that's it. No more after this, except for the ones you get to do by yourself. So I very purposely made the 2 of the last 3 examples have negative radicands because I want you to be comfortable with that, again, that point that you can have negative numbers inside of a root, provided that it's an odd flavor of root. So as you scour your list of fifth powers, did you find it? 1024. And because it's a negative, we're going to have 2 times the fifth root of what? There you go. -1024 times 2. Remember, always feed the negative into the future jailbreak. You basically saying you're going to get out of this place, take the negative with you, sucker. All right. So when -1024 gets fifth rooted, what do we get? -4 breaks out. So your jailbreak in this case is -4. So you wind up with -8 fifth roots of 2. Got it? So it's not nothing to it. All right.